So in this lesson today, we're going to learn about exponential growth and decay functions. We're going to combine these two sections together because they really are the same thing and they should be treated together. Previously, we've learned about line parent functions, we've learned about parabolas, we've learned about absolute values, we've learned about cube functions, we've learned about square root functions, we've learned about cube root functions. Today we're going to learn a new type of shape. It's called the exponential growth shape, growth and decay. We have this equation here, y is equal to 2 to the x power. This is not to be confused by y is equal to x squared, which is our classic parabola. In this case, 2 is the base, x is the exponent. In this case, let's look at a table. We see that every time the x value increases by 1, the y value doubles. And that makes sense because basically the exponential function, 2 to the x power, means that every time x increases by 1, we're multiplying by another 2. So that's what we see here. We see that the y value grows. So that's what we see in the table. The graph visualizes this same concept. Every time we move over to the right by 1 unit in the x direction, we double the height of that point in the y direction. The y is equal to 1 becomes 2, then it becomes 4, then it becomes 8. And it's all according to this factor of 2 here. This number 2 dictates how fast we're growing every time we move over by 1 in the x direction. That's why we call this a growth function. Now, on the other hand, we have a case of y is equal to 1/2 to the power of x, and if we make a table, we'll see that every time, instead of it doubling, we're dividing by 2 instead. We're multiplying by 1/2. Another way to write this would have been times 1/2 for every single hop in the x direction. We're decreasing by a factor of 2, we're dividing by 2. So we could see here the graph is decreasing. We start at y is equal to 8, we go over by 1 x unit, it goes down to 4, then 2, then 1, to 1/2, 1/4, and it's going to get very, very close to this x-axis, but it's never going to touch it, it's never going to reach 0. 1/4 will divide and become 1/8, then 1/16, then 1/32. It'll never actually become 0, and so we call this our asymptote right here because it will never actually cross this invisible line. This dotted line is not really part of the graph, but it indicates where this blue line approaches but never actually crosses. We call this our decay function because it's falling down as it goes to the right. So let's look at kind of the standard shape here, or standard equation. Y is equal to b to the x power. And whenever b, the value b is greater than 1, it's a growth type of function. It's going to be growing whenever b is greater than 1. And for example, the previous one, y is equal to 2 to the x power, that was our growth function, multiplying by 2 every time we go over by 1 unit. We have our asymptote, which is the x-axis. It's equal to the y is equal to 0 line equation. Again, our asymptote is a line that the graph approaches but never touches. In the decay case, the equation's the same, but the b value, the base, is a fraction. It's a number less than 1. So, in the previous example, we looked at y is equal to 1/2 to the x power. When, the base is less than 1, this tells us how much we're shrinking. We're multiplying by a factor of 1/2 every time we move over by 1, so we're decaying. We're dividing this by 2, or by whatever the value is, every time we go over by 1 unit. For both of these graphs, the domain is all reals. We could see that there are valid x values all along here. There's no illegal value of x. The y value for these two particular graphs are all values greater than 0. Again, it never touches the axis here, this y is equal to 0 axis, neither does it ever cross through it. So let's graph this function here, y is equal to 3 times 2 to the x power. The 2 here will tell us immediately this is a growth function that goes something like that. So we'll find 2 points, and I like to use points 0 and 1. They're easy points to plug into and calculate. So we plug these in, and then we draw our graph. Again, we already knew it was kind of a exponential growth type of thing, so we're able to draw a nice kind of curve up to the right. Let's draw in our asymptote. Our asymptote is y is equal to 0, and that's our graph. Here's another version, slightly different. In this case, let's graph 2 points. Same, x values, 0, 0, and 1. We graph that over here, and we draw our exponential graph through it. In this case, you notice because of this negative sign right in here, the graph that you might typically imagine up here, it went down instead because of the negative sign right there. We still have the asymptote that the graph approaches but never crosses or never touches either. One more thing, we're going to learn how to translate this graph. I'm adding in these little extra pieces here. We already learned how to graph y is equal to a times b to the x. Now we're going to translate that with these very familiar h and k values. So we have x minus 1 that tells us that we're translating the whole graph in the x direction by 1 unit to the right. And then the minus 3 here says that we're taking this entire graph here and dropping it down by 3. You can almost see it right here. The y value, y, is being subtracted by 3 here. Whatever it was, it got moved down by a value of 3. So I'm going to show this in 2 steps. One is we graph an untranslated version, and then we graph a translated version after that. So let's start off by graphing the untranslated version. We plot out 2 points, and we know it's a growth function because we know that the base here is greater than 1, so we know that it's going to be a growth function. Now we want to translate everything by this value 1, negative 3. So we're going to take the first point and move it over to the right by 1, and we're going to move it down by 3. So the 1 will become a 2, and the 8 will become a 5. In this other case here, we want to move the 0, 4 point over by 1 and down by 3, so this will become 1, comma 1. So those are our 2 new points. And now we're going to graph our asymptote next, and followed by the graph. The asymptote also moved down by this same translation value, minus 3. So the asymptote now is at a value of y is equal to negative 3. It used to be at y is equal to 0. The asymptote dropped down by 3, and now it's at y is equal to negative 3. Our domain in this case is still all real, but the range in this case is going to be all values of y that are greater than, or are greater than, strictly greater than, negative 3. So this is how we graph our exponentials.